Hello everyone. Good evening. My name is Siddhartha. I'm the business unit head here at Trainspace for mechanical domain. Um, Today we'll talk about conduction in batteries. Primarily, we'll talk about the anisotropic conduction within batteries. The idea essentially is we want to fully understand why do we need to move beyond the scalar when modeling batteries. So the graphic on the left that you see here, you'll see that this is an assumption that we tend to make. In many basic simulations, we treat battery as a solid uniform block where thermal conductivity is almost same in every direction. So thermal direction in X, Y, and Z all will be equal. This is an isotropic assumption essentially. This simplifies the mathematics to a large extent, but many times in very specified cases in batteries, it doesn't really reflect the physical world. Now, looking at the reality of what's there on the right hand side, this is the anisotropic assumption. The idea is batteries by themselves are not solid blocks, rather they are wound to composites. So because of this internal structure, the heat conduction itself is anisotropic. Heat is a commuter, so to speak. It wants to take the highway to move as fast as possible. So in a battery, that highway is the continuous metal foil along the winding direction. Heat travels approximately 100 times faster along the winding than it does when it tries to move radially across the layers. So today's webinar is about if our models don't account for this directional disparity, we are not making a very small error. We are fundamentally misrepresenting how batteries shed heat. So today we'll essentially talk about how to move from a simple scalar number of, hey, this is the conductivity of your material, to actually building what a conductivity tensor will look like to capture this reality, essentially. I think we can start now. So just a small background about myself. My name is Siddhartha. I've said this before. I'm the current BU head in the Wrenchwise company. I've done a master's in aerospace engineering. I have about 4.5 to 5 years of experience right now. During my master's, I worked on high-speed combustion devices, primarily towards numerical methods and computational fluid dynamics for detonation engines. I also worked on thermal system development for the said combustion devices. I carry with myself expertise in open form, both in the battery thermal system design and IC engine simulations. I have vast amount of background in technical training for CFD-driven product design as well. I have worked with a lot of companies, automotive industries. I've worked with the furnace industries to help them migrate from one source code to another, meaning that if the company wants to switch from this ANSYS to they want to do open form, that's where essentially I come in. I've helped a lot of companies transition from a lot of heavy, expensive software to something as quite advanced and quite necessary to in today's day and age, open form or other open source tools. So that's about my background. Today we will essentially talk about this topic itself. We will try and understand how do we move beyond this particular scalar. Actually, we're talking about this understanding of how does isotropic work versus how does anisotropic work. Well, in standard terms, when we talk about it, isotropic essentially means that the conduction is same in all directions. Whereas when we talk about anisotropic, we'll essentially see that the layers of batteries that are essentially made, the conductivity across these layers is going to be different versus how the conductivity is in the each individual layer itself. So in essence, we will talk about what this phenomena is all about. Before getting into the understanding of the conductivity itself, I wanted to discuss this very interesting sort of taxonomy of uncertainty in numerical simulations. This is a fundamental concept in CFD. It breaks down the errors, the unknowns that cause a simulation to deviate from real world reality. We have divided this into three different segments here. There's data, there's physics, and there's numeric. Data essentially talks about the input that you provide. In CFD, this is often summarized by the phrase garbage in, garbage out. If your boundary conditions or initial values are wrong, the result will be wrong, regardless of how perfect your solver is or how well you've defined your mesh. Experimentally, generally speaking, with CFD, we often validate against a lot of experimental or test bench data. So if pit tube, thermocouples, these are used in the experiment. If you have at least like 5% error in between, this is still considerable, saying that CFD has reached close to what real scenario still is. Many times it happens that you simply don't know what the condition is, meaning that you don't know what is the turbulence intensity. You might not know what is happening at the particular instance. So this gives rise to a lot of human errors, such as inputting the wrong fluid density, inputting the wrong boundary conditions, using inches instead of millimeters, so on and so forth. So this is what the data branch essentially talks about. Next, we have the physics branch. This is the blue one. So this refers to your modeling choices themselves. Modeling choices meaning that what models, numerical models, are you using to approximate real world physics mathematically. So a computer cannot solve every single molecule's interaction, so we use approximations anyway. So there are these reduced models. In CFD, often use these turbulence models. There's the wall solving versus wall modeling. So wall modeling, your epsilon family of turbulence models in Reynolds averaging, that's where place. Whereas the wall resolving with your omega and your hybrid DDES, LES, etc., hybrid DDS, DES, these models will use omega model near the wall. So the wall modeling aspect of it, these will essentially simplify the physics to make calculation affordable, because omega model, you need more amount of cells near to the wall. So this gives rise to some amount of error anyway. Then there is the aspect of homogeneity, assuming fluid is perfectly mixed or isotropic when it might not be. Similarly, if you are missing out on any amount of physics that you have not taken into account, neglecting a phenomena that actually matters, something like ignoring radiation in a high temperature combustion simulation, or if you are ignoring gravity in a multi-phase simulation, they will give you errors fully. There is also the concept of fluctuation of material parameters. This is primarily, I'm talking about, let's say, some thermal conductivity. Thermal conductivity varies with respect to temperature when temperature goes beyond a certain threshold. If your simulation doesn't take into account how thermal conductivity varies with respect to temperature, you will see the wrong results. So it's a lot back and forth between the safety engineer and the solver to fully describe what your actual physics is, and then try and approximate how you can solve it in the CFD solver package. Ultimately, we have the red color branch. This is numerics. This is mathematical errors, because we are solving continuous equations, essentially the Navier-Stokes equations, on a discrete grid. What we want to do is essentially we want to capture gradients as well as possible. We want to understand how the fluid is moving from one point to another. That's why we have mesh, etc. Speaking of mesh introduces a lot of discretization errors. So if you have highly curved geometries like a turbine blade, this may end up with flat cell faces. This is called faceting. Or you may also introduce inaccurate elements itself using a mesh that is too coarse or highly skewed. These will fail to capture the gradients that we actually want for boundary layers or for shock waves, etc. Similarly, since computers cannot afford to store every single data point in very high precision, there's also the round-off error, the truncation error, the iterative swing itself. Round-off error meaning that computers have the finite amount of precision, the floating point. Small errors can actually accumulate over millions of iterations. Similarly, there's the truncation occurs when higher order terms in the Taylor series expansion are dropped to discretize your equation. Your first order versus second order, etc. Then ultimately the iterative solving itself, if the simulation doesn't converge, meaning that the current iteration versus the previous iteration, if the residual between the two or the amount of error between the two has not dropped beyond a particular threshold, then it is safe to say that your simulation is not numerically accurate. because you want the values to drop beyond a certain threshold of 10 power minus 6, 10 power, and so on and so forth. So ultimately, in professional engineering, this diagram represents a roadmap for verification and validation. Verification, are we solving the equations correctly? Validation, are we solving the correct equations? That's the whole point. So essentially today we'll talk about these topics here: why average properties fail, governing equations, the calculating the effective properties, discretization errors, and ultimately one case study. We'll bring everything together by a side-by-side comparison of a 21,700 cell at a 5 seats charge rate. We'll essentially demonstrate how an isotropic model can reveal close to 13-14 degrees higher peak temperature compared to the isotropic model. Okay, so let's talk about the most common mistake that is made in battery modeling. This is the scalar trap, so to speak. Most standard CFD solvers default to isotropic properties, where you define thermal conductivity as a scalar number. So K is equal to 20 watt per meter Kelvin or 30 and so on and so forth. This approach assumes that heat flows with equal ease in all directions. However, as we can see from the image itself, the assumption is actually quite wrong. Inside a battery cell, you are dealing with approximately 1000 to 1 disparity ratio between components. So on the top, you see the aluminum foil. This is the highway, meaning that aluminum foil, the current collector, this is highly conductive, approximately 200 watt per meter Kelvin. Whereas on the wall, let's say you have a polymer separator, which acts as thermal insulator, which has the conductivity of approximately 0.2 watt per meter Kelvin. So to put that in perspective, the separator is 99.9% less conductive than metal foil sitting right next to it. So if we use a single average scalar number, you are mathematically saying that highway and the wall have merged together. You're essentially saying that solver that hey, insulating wall does not really exist. So the consequence of this error is quite massive. So by ignoring this internal resistance, an isotropic model can lead to 2000% over-prediction of radial cooling. In the winding direction, this is the coil in between. It can easily bypass the insulator by traveling along the foils, but in radial direction across the radius, the direction we often rely on cooling your radial direction. Heat must cross every single layer of your battery, including the insulating separator layer itself. So if you count for this difference of conductivity between the layers, your simulation will tell you that, hey, battery is shedding heat perfectly, everything is great, you can go ahead with your design. You make the design and you figure out, hey, physically what I measure right now is much more than what I'm seeing, in CF. So there will be errors there. So the directional disparity here essentially talks about if you have, metal separator. So tangential direction, the conductivity will be quite fast. Radial direction, conductivity will be quite slow. I think I need to change my dongle here. It's not working properly. Cool. I'll just play this once more. Yeah. So the directional disparity essentially talks about this difference between your materials within the battery. So aluminum, your heat will cross very easily, but between the layers, the heat will take a very long time to essentially move. Cool. So this gives rise to us trying to understand now what your governing equations can be from a scalar to a tensor. Now that we know that a single scalar number will fail to capture this battery physics, we take a look at mathematical solution. On the left side, you see the standard scalar Fourier's law. This is governing equation used in most basic thermal models. It is the simplified view where heat is predictable. It simply flows downhill, where temperature on one end will be higher, temperature on one end will be lower. The heat will flow from top to bottom. That's the whole point. This is fine for uniform material like a solid block of aluminium, but it is insufficient for a complex layered structure of your battery. So that's where we move to the conductivity tensor here. Here the thermal conductivity is no longer a single number. Rather, it is replaced by the matrix. Mathematical shift essentially allows us to account for the fact that heat will always seek path of least resistance. Meaning that if the thermal conductivity in xy, xz is much better than yx, yy, yz, and so on and so forth, heat will generally prefer to move in that particular direction because the conductivity is much higher there. So heat will actively try to steer itself toward highly conductive metal foils. That's the point. So the matrix on the right hand side that you see here, the diagonal terms xx, yy, and zz, these terms define conductivity along your principal axes x, y, and z. In battery, these are set to represent the high conductivity of the highway, the winding direction itself, and low conductivity of the wall, the radial direction. Everything away, the off diagonal elements here, x, y, x, y, x, y, z, z, x, z, y. These are kind of critical for high fidelity. They handle the coordinate alignment and vector rotation. So these off diagonal terms are essential because in real world battery pack simulation, your battery cell is almost never perfectly aligned with your rectangular global grid of your mesh. So without a tensor, the simulation cannot correctly rotate the heat flow for the internal foils. This will lead to a lot of errors. So implementing thermal conductivity as a matrix or tensor, essentially, we ensure that the mathematics, the representation of the physics and the structure of your battery is accurate, regardless of what your mesh is actually trying to do. Basic view of isotropic, whereas next we have anisotropic. So there is directional dependence on how the temperature variation is between one point to another and how your heat will flow based on what the thermal conductivity is within each individual layers. What is the thermal conductivity disparity ratio between the battery's highway and the wall, the aluminum foil versus polymer? Correct, this is 1000 to 1. So again, I'll just very quickly just talk about it. So using a single scalar number k is equal to 20 is mathematically averaging your thermal properties, leading to a very high number of or high percentage of over prediction of your radial cooling. So we should not do that, is the point. Cool. So now that we've looked at some mathematics, let's look at physical reality as well. The slide essentially shows you the anatomy of what is actually happening inside your cell. Inside your cell, we look at it as this jelly roll, the internal structure of a typical lithium-ion cell here. So to understand heat flow, we have to look at the disparity between these layers. So the conductors, you have the copper anode current collector at very high, 398 watt meter Kelvin. There is the aluminium cathode conductors is 237. These are places where heat will flow very easily. But at the same time, you have this bottleneck as well, sticking right in the middle. This is your separator. The separator is very essential because if your anode and cathode, these two mix together, they might burn, they might release a lot of heat, and they also require a separator to move the ions between the two. So separator being at very low thermal conductivity when compared to copper, which is sitting right next to, this creates two very different paths for your heat. So in the wind direction, the tangential direction, heat can effectively bypass the separator, traveling almost entirely through the continuous highly conductive metal foil. However, in the radial direction, as we move from top to bottom here, it becomes very difficult for heat to move forward because the thermal conductivity itself is very low. So in radial direction, the heat has no choice. First, it must cross one of the foils or every single one of the jelly roll itself, and then it will pass over every single one of those insulating separator layers. So this is the structural reality of a battery. When we talk about anisotropy, we essentially mean that physical arrangement of materials forces the heat to behave differently. This is depending on, again, which way heat is trying to. If your model assumes average conductivity, it will again ignore that separator is a thermal wall in a particular direction, but virtually it is non-existent in the other direction. One of them is a conductor, one of them is an insulator. Heat will prefer the metal highway, and moving from top to bottom of your bottom to top, let's say the copper foil all the way to your aluminum foil, this will take a long time for the heat to move. So how do we do the calculation now that we sort of understand there are multiple materials, we should account for thermal conductivity. How do we actually calculate these values for our simulation? To do this, we use the rule of mixtures, so to speak, to determine effective properties of the jelly roll itself. So on the left hand side, we see that when we have parallel flow, so arrows actually moving in the parallel direction to your roll cells, it represents heat moving along the winding itself. So think of this like resistors in parallel. So because you can choose the path of least resistance, it flows predominantly through the highly conductive metal foils. So to do this, we essentially say that, hey, K parallel is equal to, phi, essentially volume fraction of your each material here. So phi times the thermal conductivity of each material, you can just take a sum, and this will give you a parallel thermal conductivity for your entire battery. Whereas if you have normal flow where heat is trying to move across the layers, in such a scenario, the resistors are connected in series. In this direction, heat is essentially trapped. It cannot bypass the insulating layers and must pass every single one of them. So we calculate this using the harmonic mean. This is again, phi is your volume fraction of each material, and the 1 by summation of phi divided by the thermal conductivity. So to understand how much this actually matters, you can see the example at the bottom here. So making 50% along with 50% elastic, in parallel, your thermal conductivity could be close to 200, whereas in normal direction, it could be very close to 0.5, 0.4 per meter. So the difference is, close to 500 times, which is, quite absurd, so to speak. This gives rise for you to understand, if you are in the early stages of a project and you don't have the exact volume fractions of every foil thing, good rule of thumb is assume 1 to 20 ratio between radial axial conductivity to avoid the scalar. But do try to account for individual thermal conductivities of all the materials which are present inside your particular domain. So in plane, we see the effective thermal activity through this formula. In normal, the through plane, this is the series, and the K effective is given by this particular formula. There is one other concept here that really comes into play when you want to run high fidelity models. This is the geometry mismatch. Getting the material properties right is absolutely necessary, but also understanding how your geometry needs to be treated is also very necessary. Most CFD solvers operate on Cartesian mesh. This is to say that the globe grid is aligned to your X, Y, and Z axes. Given that batteries, for the most part, are cylindrical, it is logical for us to think in the R theta, and Z terms for the cylindrical coordinate system itself. So, as you can see on the left, this creates a major conflict in that if heat is flowing perfectly along in the global Y direction, simulation is straightforward. But as you move around the circle, same radial flow becomes a complex mix of both X and Y coordinates or X and Y normals together. So without a way to communicate cell's circular physics to the rectangular grid, anisotropy just created actually becomes useless. So solution is to implement something called the local coordinate system itself. So we define the cell in terms of cylindrical coordinates. We can tell to the solver exactly which way files are actually wound. To make this work, the solver must use a transformation matrix, this R transformation matrix. The idea essentially is we mathematically rotate tensor at every single time step, mapping those local properties on the global grid. The takeaway from this slide should be, local coordinate system axis must be perfectly aligned with the battery winding axis. If that is not done, so for example, in CFD world, we often deal with slight misalignments anyway, but physics is quite unforgiving because difference between hive and wall is so vast. What we've seen for 1000 to 100 to 1, so on and so forth. Even a 1 degree tilt of your battery away from the coordinate system, this will actually break the physics. So this effectively leaks high conductivity of winding into radial direction. causing your model to overpredict your cooling, let's say, giving you a sense of force safety. So always verify the axis of rotation before hitting solve. That's the whole point. So mapping your cylindrical to Cartesian in the radial direction. So the x and y components, this is taken care of to the solver. So when solving for the battery research, the solver must rotate this tensor every second. So what is the number one cause of physical error when setting up a local coordinate system for an anisotropic battery model? So we have good idea about material properties. We have an idea about, how to calculate these properties. Then we also saw the geometry mismatch. Now we moved to the technical side of it, where we want to discuss the discretization, the flux leakage. This is where high fidelity battery models tend to fail. So when we introduce high anisotropy into a model, we are not just changing material properties, we are fundamentally changing how your series solver is perceiving the geometry. Mathematically speaking, high anisotropy behaves exactly like a severely skewed mesh, meaning that even if your physical mesh looks perfectly rectangular, the numerical equivalence makes it much harder for your solver to reach a stable solution. So to calculate your heat flux between two neighboring, cells here, the solver must perform decomposition. It splits the flux into two distinct parts. There's an implicit, there's an explicit. Implicit part represents stable, predictable flow directly to the neighbor cell. Explicit part handles the sideways or off axis caused by anisotropic terms themselves. So there's always going to be some balance between these implicit and explicit terms here. If you have high anisotropy, explicit correction will begin to dominate the implicit part. And if explicit term becomes too large, your matrix becomes unstable. And this is where battery simulations tend to see a lot of oscillations in their residuals. So it's physically impossible. You'll get physically impossible results like negative temperatures and so on and so forth. So let's take a look at how can we, fix those. So if you have the two cells here, actual flux may be happening in a particular direction. So flux doesn't point at the neighbor itself, and CFD solver will have a harder time to map how to move your heat from one point to another, because our thermal conductivity itself is anisotropic, defined by a tensor. So cross diffusion terms. The idea essentially is to understand why your simulation might be struggling. You can take a look at this, slanted root effect here, slanted roof effect. So standard isotropic material, vertical temperature gradient only moves heat vertically, but in anisotropic, the vertical heat gradient actually can drive horizontal heat flow as well. This occurs because the internal highways of your metal foil redirect this energy along their own orientation, regardless of the primary gradient direction itself. On the right hand side, you can see how this is calculated. The total heat flux in the x direction is no longer just a function of x gradient. It is now influenced by gradients in the y and z direction as well. So heat flow in just the x direction is no longer just negative k, nabla t. It is also consisting of the k individual thermal conductivities in xx, xy, and xz. So essentially, we talk about these interactions of your cross diffusion term ultimately, because these terms are quite complex. Most CFD solvers cannot handle them within the main stable calculation. Instead, they try to solve it as a separate explicit side of the equation. Again, if these explicit terms become too large, this will, become unstable. Your residuals will oscillate a lot. So sources essentially say that if you see these oscillations, you lower your energy relaxation factor. Relaxation factors helps in managing the oscillations between your iterations. So if you start seeing spikes in your energy equation, keep your relaxation factors to somewhere around 0.9, 0.7 to stabilize this matrix, and then later on you will see that your oscillations have slowed down. But one disadvantage, so to speak, for introducing your relaxation factors is that your simulations become a bit slow, because you are essentially telling the iterative solver to slow down. Let's not go beyond a certain bound, and we will just take it slow. So for that reason and that reason alone, we want to use the energy relaxation factors. If not, no need to worry about it. So the cross diffusion physics. So if you had the simple gradient between your two layers, it would be the yellow line, but generally it is not the case. Generally it is this red color line which is slanted. So the tilted layers and isotropy, all of this will play a huge part in how your heat will actually flow. As we sort of understand the technical implementation, let's look at the fidelity itself of what you want to achieve here. You want to understand how we can balance accuracy versus the computational cost itself. In battery thermal modeling, there are three distinct levels of maturity, and choosing the right one for your project is very important. Level 1, this is smeared scalar. This is wrong but fast approach. So when you're trying to build a product from scratch, generally this is used very, for early sizing itself. It relies on isotropic assumption. We use single conductivity number the entire cell. It runs very quickly, consistently going to under predict the core temperature, because again it ignores the internal insulating layers. You should use level 1 for very early stage sizing when you just need ballpark figure. So when just your project starting, you can just use this as a kickoff point, so to speak. Level 2, this is orthotropic continuum. This is generally the recommended industrial standard here, and it is sort of the sweet spot between level 1 and 3. So by using the solid mesh combined with the tensor properties on a local coordinate system, we can actually achieve highly accurate core temperatures, often with little as 2%, 3% error. So this also keeps your mesh counts manageable for full pack simulations. This approach respects the internal highway and the walls without needing to model every microscopic layer, essentially. And level 3, this is the explicit geometry. This is physically perfect but impossible for most commercial applications. This method actually involves meshing every individual foil and separator. So it will give you the absolute ground truth, but a single cell would require billions and billions of elements. This makes it computationally quite impossible for a full battery pack. This level is generally reserved for academic research or microscopic failure analysis. So the takeaway is quite clear. We should be using level 2, the orthotropic continuum itself. It provides the fidelity needed to catch thermal issues that level 1 is going to miss without the overhead of your level 3. So isotropic, fast, wrong, orthotropic, industry standard, and explicit layering, quite impossible. So we understand what we need to model now. We've essentially understood the internal physics of your cell. We have taken a look at how heat actually leave the battery. There is a problem of interface. Even the most accurate anisotropic cell model will actually fail if you don't correctly model the thermal interface materials, or TIM. TIM essentially sits between your cell and the cooling plate. On a microscopic level, no two solid surfaces are perfectly flat. As you can see in the details here, you can see the crest centrops that we have made in here with the cooling plate and with the battery cell itself. So at this thickness, the material has enough volume to justify its own cells in your mesh for the most part. And between this gap, ultimately, the microscopic gaps are filled with air. Now, air is actually a very poor conductor of heat. It is a very powerful insulator. So we tend to use thermal interface materials. This can be a thick pad. This can be paste. If you are using a thick pad close to like 0.5 mm, we should mesh it as a solid volume itself, because this material has enough volume to justify its own cells without compromising numerical stability. Whereas if you are using paste, this is where you do not attempt to make the mesh for a thin layer of paste somewhere lesser than 0.1 mm. If you try to create less than 0.1 mm cells, you'll end up with very high aspect ratio cells. These high aspect ratio cells are going to be introduce a lot of errors perhaps, and they'll very quickly reduce your time step to a very unrealistic number as well. This is probably the leading cause of simulation crashes, massive numerical errors, etc. Instead, what we want to do here for pastes is something called contact resistance boundary condition. So instead of physical geometry, we want to represent the paste as a mathematical resistance defined by its thickness divided by its conductivity. So this approach keeps your mesh also clean and your simulation also stable. So having said all of this, let's now try and move towards one state of isotropic versus anisotropy. So essentially the gap versus TIM here. Between cells, there will always be these air gaps which will act as insulators. We can use thick pads, we can use paste. So if it is thick, greater than 0.5, you mesh it as a solid. If it is less than 0.1, you just introduce the contact resistance boundary condition. Yep. So here anisotropic simulation begins to diverge or shows numerical oscillations. Which settings should you use to lower, should you use to stabilize your particular metrics? So temperature gradient, mesh aspect ratio, energy relaxation factor, or copper conductivity. Yes, it is the energy relaxation factor. Okay, so now let's talk about this case study itself. To bring everything we've discussed into focus, essentially, we'll take a look at this cell that we have. This is 21700 cell during a high power 5C discharge event. Essentially, this comparison is going to highlight the real world danger or scalar trap that we saw in the beginning. So the isotropic result on the left that we see here, the standard scalar model is splitting a peak core temperature of 45 degrees Celsius because this model assumes that highly conductive foils are mixed with insulating separators. It will mathematically assume that radial cooling is much more efficient than it actually is. So in our design review, we saw that it was flagged as safe, but this can potentially lead to engineering team approving a thermal management system that is fundamentally inadequate. When compared the same result to the anisotropic model, this is our high fidelity model that we developed. So essentially, this reveals a much higher peak temperature, 58 degrees Celsius. So we accounted for the 1000 to 1 disparity ratio and the fact that heat must always cross every single insulating layer to escape into your nearby cooling systems and whatnot. So we see that the core is actually much more hotter than the simple average is what is showing us right now. So there's a disparity of 13 degrees Celsius prediction error. We see 45 degrees is the standard operating temperature for this particular type of cell here, but the 58 degrees Celsius, this will significantly accelerate aging degradation through battery chemistry itself. So this is the cell. This is 21700 cell during 5C discharge event. The left hand side, this is the isotropic model. We saw the maximum temperature to 45 degrees Celsius because the isotropic model assumes that between the layers of your cell, the thermal conductivity is equal to how it is moving in the tangential direction to your radial direction, which was incorrect. The max temperature we predicted was 45 degrees Celsius. Compared to the anisotropic model, which gave us a core max temperature of 58 degrees Celsius, we had a disparity of 13 degrees Celsius here. Primarily speaking, for this type of cell, the 45 degrees Celsius is standard operating temperature. So a design team will actually, or a product design team will actually look at the CFD model of isotropic and say that, hey, my cell's maximum temperature is 45, we can still work with it, maybe we'll just use air cooling. Whereas if you accurately predict using the isotropic model, the design team take a look at it and understand that perhaps air cooling is not the best thing to do. We still try with other methods of either liquid cooling or some other method of phase change materials, so forth. Because 58 degrees Celsius is significantly going to accelerate the aging and degradation of your battery chemistry. So key takeaway here, essentially, again, relying on isotropic models is great. You have to begin designing your product when you want quick results to explore your design space. You can couple that with an optimizer and essentially understand what parameters work for you. But if you are already interested in the high fidelity, you want to accurately predict how your cells may fail, you absolutely need to consider the anisotropic nature of your thermal conductivity itself. Again, if you don't account for it, your simulation will just tell you, hey, battery is fine, and in the reality, physical reality, you will see that it fits the field. So that's that. So yeah, ultimately the isotropic model giving us 45, anisotropic giving us the hotspot in between, and isotropic model is going to hide this particular hotspot. So key takeaways from our side. Use tensor properties, align the coordinate system, and numerics. Please manage your solver stability as well as you. I'll just quickly talk about these points here, and then we can perhaps wrap up. Essentially, to conclude, dive here is the final checklist that we have. Material, never use a single average number for thermal conductivity. Implement the conductivity tensor. Apply the rule of mixtures. So use the K parallel to model the high conductivity. Use the K normal for the insulating walls. And if you lack the material volume fractions, the phi value, conservative starting point is 1:20 between real and axial conductivity to avoid the initial scalar wrap itself. Then we have the geometry itself. You must always implement a local coordinate system that perfectly aligns with the physical axis of your winding or the battery winding. Tilt axis is leading cause of simulation errors. 1 degree misalignment can actually cause solver to predict the heat flowing in a different direction or leak the heat incorrectly. This will break the physics. And ultimately, if you are using the isotropic model, there is always the cross diffusion instability. If you notice, so yeah, just to clarify, even if your mesh is perfectly valid, if you don't have, if you have very good skewness also, if you have very good orthogonal value, and so on and so forth, but numerically speaking and mathematically speaking, the high anisotropy ratios still behave like meshes, which will lead to cross-section instability. So if you notice the numerical oscillations, first thing that you want to do is lower your energy relaxation factor. So initially, if you started with 0.9, maybe reduce it to 0.7. This will give the solver necessary stability to reach a convergent solution. Ultimately, accuracy is in anisotropy, safety is in the interface. Internal anisotropy ensures that your core temperature prediction is accurate. Your attention to the interface itself ensures that this heat can actually be removed very safely. So by following these best practices, you can actually make your simulations much better. One final I guess this is for helping me rate this particular webinar. Please let me know how did you find it. So I just take a small pause and try and understand, do we have any questions? So thank you very much for joining. The next webinar we're going to have, this is on Friday. We will, in a similar fashion, talk about radiation heat transfer. Radiation becomes much more relevant. Your temperatures become higher than 400 degrees Celsius, which is generally what happens during thermal runaway. So if you experience thermal runaway in your battery pack and you don't account for radiation heat transfer, that will very vastly underpredict again the temperature or localized hotspots within your battery pack itself. So next week we will tackle more about that. Oh, brother, sorry. Next we are going to do convection, if I'm not wrong. With the air cooling versus liquid cooling comparison, we'll show one simulation, and then the next week prior to that, there we'll do radiation. So sorry about that. Please keep a lookout on our LinkedIn page. We also have YouTube, Instagram. If you're interested, you can join the next webinar as well. I will urge you to join because we'll again cover one other fundamental mode of heat transfer for battery packs. Great. It's been a great session. Thank you very much. And that's all from my side.